One more figure that I want to share with you before we switch over to learning how to run the R code and write the R code to make these figures. So one of the principles in social science is that when we're running regression models on observational data, meaning we didn't run an experiment, we're trying to look at the world as it is, measure some phenomena, and understand the causal relationships between them. When we're in that world, there's usually a bunch of different reasonable ways to specify the regression we want to run in order to test our hypothesis. There's a bunch of different ways we can measure our independent variable of interest. There's a bunch of different ways we can measure our outcome or our dependent variable, right? And then there's a bunch of different statistical controls we can include or not include and trade-offs associated with doing that. And there's often even different estimators we can choose, right? Different ways of specifying the regression equation. So among all these choices, right, how do we choose one model and call that the regression that's going to tell us whether our hypothesis is right or not? The answer is the best way to do things is not to choose just one, right? The best way to approach this is to run your analysis a lot of different ways. Say, okay, there's a bunch of different ways to do this, all of which are reasonable. So let's do all the things that are reasonable. And then if our result holds across all these different reasonable choices, then we start to believe it's real. And if, depending on which of these reasonable choices we make, we're getting different results, then we have to be a little bit humble and we have to acknowledge, you know what? This analysis we're running isn't telling us whether we're right or not. We're not gaining certainty here. What we have is we've got conflicting information and we just need to acknowledge that this is mud and we don't know what the truth is, right? So, in this particular paper that this figure is from, we were looking at the relationship between economic structure, and particularly whether a country is more land-oriented, getting a lot of their income from natural resources and agriculture, or whether they're more production-oriented, getting their income from manufacturing and services, right? And depending on what their economic structure is, that affects whether they want to go seize more territory, right? If you're very land-oriented and dependent on agriculture and mining and oil extraction for wealth, then you're already optimized to extract wealth that way, and seizing more territory is a pretty efficient way to become wealthier, right? But if you're more production-oriented, if you're all engaged in manufacturing and services, taking more territory, yeah, sure, it's still good, but the opportunity cost is higher and the benefits are not as great. So we think that production-oriented states are less likely to engage in military conflict over territory, and that's the key hypothesis we're testing here. Now, there are a variety of different ways to measure land orientation, and we developed a measure of land orientation ourselves in this paper. This is a SPEC lab product, right? But we still have a variety of different ways to measure. We've got 3 different dummy variables and 1 continuous variable, all of which are measures of the same theoretical construct. And then on the dependent variable side, on measuring military conflict over territory, that we can measure a lot of different ways. Do you make territorial claims that are resource-based? Do you make any kind of territorial claims at all? Do you fight militarized interstate disputes about either of those types of claims? How many claims versus do you make them or not? How many conflicts versus do you have a conflict or not? Are you part of a territorial rivalry? We came up with 10 different ways to measure this. And then there are a variety of different control variables we could use or not. It was really important to control for regime type, whether you're a democracy or not. Guess what? There's a few different ways to measure that, right? And then there's, controls that you either include because they seem important, like trade, but you might want to leave trade out if, because we don't have great temporal coverage going back in time. We actually don't have data on trade volumes for a lot of countries back in the 19th century. So, so there's trade-offs to including that as a control variable and losing a lot of observations. We ended up running 160 different regressions here, right? 10 different measures of the dependent variable, 4 different measures of the independent variable, and 4 different sets of control variables. We could make 16 different regression tables with 10 models each and put those in a very long appendix. But again, that would sort of be a signal to people that we hate them as readers. And what we really want to do is summarize the results of these 160 models all in one place. What's the result we care about? And really, what we care about is just this coefficient on land orientation. We care how big it is and whether it's statistically significant. And so that's what we want to summarize, is just 160 coefficients. Okay, we can make a figure that summarizes 160 pieces of information, right? So how we organized is we said, okay, let's organize this by different ways to measure the dependent variable. So each row in this figure is a different measure of the dependent variable. And for each of those, we run the model 16 different ways with different measures, the IV and different sets of controls. And what in the information we report about each coefficient is numerically how big is that coefficient. And then is it statistically significant? And if it is statistically significant with a p-value of less than 0.05, we use one of these little gray rectangles. And if it's not statistically significant, we use a little black square. And you'll notice that like the heights are slightly different with these gray squares and things. We used a jitter function so that even if these things were supposed to be right on top of each other, we moved them just a little bit so that you could see each of them. So that's why they're sort of situated like this. And we put a box plot over top of it to kind of see, well, where is the bulk of the data here? So that's what's going on in this plot. And it's a way for us to summarize 160, the results from 160 regressions in one nice clean figure. And the way what we're transitioning to in the next video is, well, how do you start to extract the information to do this? And again, we're pulling out the coefficient, right? So that beta hat, and we're pulling out the standard error, or that measure of uncertainty. And from those, we'll also pull out the p-value, which is what we're using here to distinguish between significant and not statistically significant results, right? And with those pieces of information extracted from these regressions, right? So we need code that runs these 160 regressions, and then from each regression pulls out this, the coefficient size and the p-value, and then feeds those into a new data frame, right? That's going to have 160 coefficients and 160 p-values, and then we can plot those coefficients and p-values into a picture like this. And so that's what these next videos are going to do, is how do you pull out those coefficients, those standard errors, those p-values, those confidence intervals that you're going to need in order to make the pictures that you've just seen in these first 3 videos. Looking forward to it.